One is that the line is very wide, more than 50 kilometers per second in the wings, and is very bright, with brightness temperatures in many tens of kelvins. And it's sharply peaked at the position of essentially the Kleinman Low Nebula, which was known to be a site of active star formation. So this immediately showed that there was a close connection between CO emission and star formation. Here's the telescope, not the one they used actually. This is the 12-meter surface that replaced the old 36-foot, and which when NRAO abandoned it, they gave it to Steward. And now we have this wonderful ALMA prototype antenna. So remember, we have a beautiful 12-meter state-of-the-art on Kitt Peak, thanks to the efforts of Lucy Zuras and a lot of very hard work by the staff of the ARO. And so by using telescopes like this, observing molecules, we can get a great deal of information about the sizes and shapes and distributions of clouds, their dynamical states, temperature and density, even sometimes magnetic fields, the abundances of different chemical species and of their isotopes. Now, molecular hydrogen is, of course, the main species, but the problem with that is it's so symmetric. It has no dipole moment. It has no radio frequency lines. There are quadrupole transitions in the infrared, but the upper state energy is so high that they're essentially never excited under normal conditions. So we have to use some kind of tracer molecule to study the molecular gas. And I think most people who are in this game would agree that CO is really the best overall tracer. There's no single universally useful tracer. They all have their limitations, but CO has a lot going for it. One is it's the most abundant after hydrogen. It's a tough molecule. It takes over 10 eV of ultraviolet radiation to break it apart. It has a simple spectrum with a number of lines that we can observe from the ground. It is readily excited by collisions with H2, and it has some isotopes, which, because these are rotational transitions, are very well separated in frequency, so we can observe them independently. And even though 12C16O, the main form, is often very thick, the rare isotopes are not. So there have been extensive surveys of CO, and it's been a very good tracer of the overall molecular content of the galaxy. This just shows the rotational levels of the molecules, and today I'm going to be talking, well, the first one that the Bell Labs group discovered was the ground transition from about 5.5 kelvins above ground. Most of today's talk will be about the 2-to-1 transition, which has an upper state energy of about 16.5 kelvins. And I'll show some data of the 3-to-2 transition, which comes from yet higher energy levels. But these are all quite accessible from ground observations. One of the things that was immediately apparent, too, from early observations was that the 12CO must be very optically thick, because the ratio of the 12CO to 13CO intensities were down in the range of a few. And if the lines were optically thin, they should approach more like 50 or so, the isotopic ratio in the ISM. And so that tells us 12CO usually has an optical depth of at least 10 or so in most typical observations. And that can be both an advantage and a disadvantage, as we'll see. So today I'm going to highlight some work from a whole series of studies, which in that kind introduction, people pointed out we've been doing for about a decade now, using our own radio telescopes, mostly the sub-millimeter telescope on Mount Graham, a number of giant molecular clouds, low mass clouds, and some Bach globules, including a number that were observed by Amy Stutz for her PhD work here, and also even clouds near supernova remnants, such as a survey that Charlie Kilpatrick did for his dissertation a few years ago. So here's the telescope, the Heinrich Hertz submillimeter. We call it the SMT, a 10-meter precision surface up on Mount Graham. And it's a very fine telescope, state-of-the-art, even though it's now going on 20-some years old that we've been using it, but it's a beautiful instrument and still works very well. And it now has, for several years, very fine receivers that were originally developed for ALMA, and we graciously received essentially in long-term loans from NRAO. So with this 1.3 millimeter band, ALMA band 6 mixer, we can observe both the 12 and 13C isotopes in the J equals 2:1 line, which are very readily excited in most molecular clouds. And because of the nice design of the mixers, the calibration is excellent, and we observe both isotopes through the same optics simultaneously, so we can compare the images with great confidence that there are no pointing errors. And we have spectral resolution of about 0.3 of a kilometer per second. Most of what I'll show you today has that, or a capital R of 1,000,000, if you like. And also I'll show some work done with Chris Walker's SuperCam focal plane array for the 3:2 line at 345 gigahertz. We'll use a technique called on-the-fly mapping, where we scan the telescope back and forth, and so we can get full spatial sampling and don't lose any of the large-scale structure, which is, of course, a problem with interferometers such as ALMA. And so we can derive physical properties by combining the different isotope maps as well as the maps of different transitions. So what are the questions we're interested in that these observations can help us address? First, what are the properties that relate to star formation? What is it that gets star formation underway? What conditions do we require? What sets the rates? And how do stars affect the cloud out of which they form? What are the sort of feedback mechanisms? And related to that, what is it that sets the efficiency of star formation on the smaller and also the larger scales? So now I want to just give highlights of some of the published work of different kinds of clouds, and start with the lower mass clouds. These are not giant clouds, but we picked them because they were part of a legacy Spitzer project led by Neil Evans called Cores to Disks. And they're all relatively nearby, within a few hundred parsecs. They're forming low mass stars, meaning no OB stars, so there are no H2 regions involved. And because of the C2D work, they have a very good census of all the young stellar objects with classification. So we have some idea of what their evolutionary status of the individual YSOs are. So let's start with Perseus. This is a very long, elongated structure with multiple centers of star formation. And here we're focusing on this region here around NGC 1333, which is a reflection nebula, not an H2 region. The distance, 235 parsecs, so our map has a resolution of 0.04 parsecs at the resolution that we achieve in the 2:1 lines. So just to show what the data look like, this is the peak brightness temperature of CO on the left, the main isotope. And since this line is almost certainly optically thick pretty much all over the field, this is a good measure of the gas temperature. We have good reason to think, and I'll show you why, the gas excitation temperature is in fact very close to the gas, the molecular excitation temperature is very close to the gas kinetic temperature. So there are peaks as high as 60 Kelvin here in the center. On the right side is the CO line, 13 CO line. And it's also very bright, but it's not quite as bright as the left side. So that tells us this 13 CO is really not fully optically thick. It's probably has optical depth of order unity in places. If we look at the integrated line intensity on this slide, the picture is similar, but not quite the same. And on the right side, the 13 CO now, the integrated brightness temperature for a moderately optically thin line is a pretty good measure of the overall gas column density distribution. And I don't have time to go into the details for this particular source, but I'll show you examples of that in a minute on another object. So with this data, we can also look at the kinematics of the cloud. And this shows the second moment, or a velocity dispersion, the line width of the main optically thick CO 2-to-1 line. And so this now shows the lit line in kilometers per second. And the symbols here mark the young stellar objects that were cataloged from a C2D survey, ranging from the very youngest, class 0, to the more evolved but still young objects of the class 3 type. So it's clear that the gas is highly disturbed in the vicinity of the young stellar objects, which are dominating the central part of this field. Now, if we zoom in on the blue rectangle here, we can look for the effects of bipolar outflows. One of the features of star formation during a certain stage is that they develop strong bipolar flows, which have the possibility of disturbing the gas in the cloud out of which the star is formed. And so this shows contour maps of the blue and red-shifted line emission for the main CO line, extending out to plus or minus 20 kilometers per second. And here the symbols are the same as in the previous one. And you can see that much of the central region where all of these young stellar objects are concentrated is dominated by supersonic outflows generated by the young stellar objects in their bipolar outflow stages. And just as an example, if we pick source 44 from the Enoch catalog, which is at the very center and currently appears to be the most dynamically interesting, we can take spectra of the CO lines at the two peaks of the red and blue shifted, and we see extremely wide wings. So this shows the main CO isotope in the solid, which is optically thick, and the wings extend far out from the line center. The 13 CO line is not optically thick, and so we see that in the dashed showing the bulk motions of the gas. The notch in the center is a well-known phenomenon due to self-absorption because there's cold CO at those velocities along the line of sight between us and the cloud, and so that absorbs some of the emission. But you can see that the line wings extend out to very large, very supersonic velocities relative to the line center. Sorry. And so what can we say about the bipolar outflows in terms of how that affects star formation? This looks to me like the formation of a low mass cluster that in 100 million years or so might look like the Pleiades. There are no massive stars, but there is strong bipolar outflow activity from a number of the class 1 young stellar objects, and they're clearly injecting mechanical energy into the gas. And the supersonic motions must be shocking the gas and producing heating and injecting turbulence into the cloud. And all of this dynamic activity is likely to at least terminate star formation in the center. And so these bipolar outflows should have some kind of a regulation effect on determining the star formation efficiency. So that's an interesting example of the kinematic information we can get from CO mapping with high sensitivity over this large region. Okay, let's move on to another one of these C2D objects in the Serpens molecular cloud complex. This is a low resolution grayscale map of extinction, and the region that was part of the C2D survey is outlined in the black and the gray here. So there's There was good Spitzer observations of that with catalogs of YSOs. And the region that we mapped in CO with the SMT is outlined in red here. This was the subject of a dissertation by an honors thesis by Kaylin Burley here a few years ago. And just to show what the data look like, this is the peak brightness temperature, again, of the main isotope. And you can see there's a strong concentration of rather warm gas in the northern part, and then a fading out as you go to the south. 13CO looks similar, but not quite the same. And so this is more, again, a measure of the overall column density of the line, of the CO line, in this case of the 13CO, which is not optically thick. Now, if we look at the 13CO integrated intensity, that should be a good measure of the overall column density distribution of the gas, and compare that with the locations of the young stellar objects from a paper in the C2D collaboration. Notice these are coded according to the different classes. So the cold class 1 is supposed to be the very earliest stages, ranging to more evolved, and then classes 2 and 3 are the more evolved of the young stellar objects. And you can see there's a very tight cluster of the very youngest stars concentrated on the highest column density of the gas. And as you go down along this long sort of filamentary structure, most of the young stellar objects here are of the later type. So it looks as though most of the young stellar objects toward the south have formed longer ago than what we're seeing the most active star formation up here, as though there's been a decline in star formation recently as we move from north to south along this structure. Let's see. And yeah, so now if we zoom in on the square here, where we see the highest concentration of young stellar objects, we can do something interesting with the kinematics. So this shows the core region in the 13CO 2-to-1 line, optically thin. And this is now the velocity centroid, or the first moment. And since the line is essentially relatively thin, it gives a good measure of the bulk motions of the cloud, better than 12CO, which is optically thick. And again, here the symbols mark the young stellar objects the same as in the previous slide. And you can see clearly there's a very strong concentration of the earliest types, the class 0 and especially class 1. Interestingly, between two regions of the cloud which have a red shifted and a blue shifted overall bulk motion, which has between them a velocity gradient of about 1.5 kilometers per second per parsec, which is a relatively large gradient within a molecular cloud. And it's striking that the strongest concentration of the most recently formed stars is in between these two regions of the red and relatively red and blue shifted velocities. So we can also look at the second moment, which is the width or dispersion. And once again, you can see very strong evidence of very highly disturbed gas motions up in the region where the strongest concentrations of the very earliest stages of star formation occur. There's also disturbed gas here, and I didn't plot them on this figure, unfortunately, but if you look back at the previous slides, there are also some rather young objects here which are still producing bipolar outflows. So overall, the star formation is producing, again, in this case, just as in NGC 1333, evidence for a lot of kinetic energy input by bipolar flows. So just to summarize what some of the dynamical effects on the Serpens region, the highest density of the earliest stages is in the northern section, And interestingly, this concentration lies on a velocity gradient, which at least is suggestive of possibly a collision of two clumps of gas, which had some relative motion, producing or inducing star formation, which we now see most actively within the last million years or so, just based on the classification from the C2D categories. And the 12 CO line widths, again, show very disturbed kinematics, so there's clearly energy input by bipolar outflows, which may also be then regulating the star formation rate. Okay, let's move on to another major topic, the giant molecular clouds. And as I said earlier, we have a number of papers that we've been looking at a number of these clouds, including the one Serena showed of the W3 region, and also with Miju Kong, some papers on W51, both giant, well-known giant molecular clouds. Today I'm going to talk about a couple of others, somewhat more recent results. These are important because they are the main site of star formation. I think it's fair to say that most of the stars in the disk of the galaxy were formed in giant molecular clouds, which then dispersed and spread the stars throughout the galactic disk. They have anywhere from hundreds to several thousand stars, and most importantly, they have sufficient mass, raw materials, that they can make the most massive stars. So giant molecular clouds, generally speaking, are about the only place you find young O and B stars. And so they're usually associated with H2 regions. So one of the key questions then, what are the conditions in giant molecular clouds that either favor star formation or regulate it or bring it to an end? One of the early papers, interestingly, after the first discovery by Wilson, Jeffords, and Penzias of CO and the very large line widths, was a paper by Goldreich and Kwan, who attempted to explain these line widths, claiming that the clouds were in a state of freefall collapse. And the paper actually has been influential, even though it was wrong. It was almost immediately pointed out that if that were true, then the star formation rate in the galaxy would be way too high compared with what we know it to be. And so giant molecular clouds probably are forming stars by what's come to be called a gravoturbulent mechanism. It's clear that these clouds are highly turbulent, supersonically so. They're highly compressible as well, so they don't behave like perfect gases in any way. And it's possible that turbulent compression can then create local enhancements in the densities, which under the right conditions can cool off. If the shape of the cooling function is just right, then that can lead to cooling and further enhancement of the density and form prestellar cores. And so there have been a number of numerical models. This is a complicated process, obviously. It's not readily subject to analytical solutions, but numerical modeling has shown a lot of promise, and I'll show you an example of that in a little bit. And so the gravoturbulent mechanism is one that seems to be currently the most favored in terms of explaining how giant molecular clouds form stars. So let's look at a couple of examples. First, one called Sharpless 235, which has an associated cloud. And then hopefully I'll have time to get to another very recent work on the so-called California molecular cloud. So Steward Sharpless published a catalog way back in 1959 of small red nebulous things, which were mostly H2 regions relatively nearby. And so these mostly are associated with giant molecular clouds because they're energized by O and B stars that have recently formed. And this is an example of a group of H2 regions toward the anticenter, distance is about 2 kiloparsecs. And this is a red plate from the sky survey. It's been colorized here to highlight the colors. But each of these H2 regions from his catalog, so there's a large one here, another pretty good size one here. This is 235 and 233 is over here. 234 is off to the south somewhere. We mapped this region over about 1 square degree in the 2-to-1 CO lines, both isotopes, and it looks like this. And now if I overlay contours of the CO on that sky survey red image, it's the same image I just showed you, except that now it's in grayscale. And you can see some interesting things here. First of all, 232 has very little molecular gas associated with it. It's the largest and most evolved. 231 is sitting in a huge hole in the middle of the clouds. So if we can blink back and forth, you can see this H2 region has clearly carved out an enormous cavity in the molecular cloud as it's expanded, compressed gas, the molecular gas here, and in fact, we've argued in another paper that this H2 region is a result of triggered O-star formation at the edge of this compressed range of gases. 235, which is the brightest region, is beginning to cut apart the molecular cloud, it looks like. And there are 2 more hotspots down here, which are also associated with B stars, as we'll see. Now, we've also observed this with Chris Walker's SuperCam array in the 3-to-2 line. And as you can see, it looks a lot like the J equals 2-to-1 map, but this is from an energy level J equals 3, which is twice as high in energy. And so by comparing the 2-to-1 and 3-to-2 maps, we can actually make some arguments about molecular excitation. So this just highlights the capability of the SMT with multiple frequency receivers to use maps of different CO transitions to, well, first of all, comparing the CO 2-to-1 isotopes, we can measure gas temperature, optical depth, column densities, and then by comparing with the 3-to-2 lines, in fact, I will show you this justifies a fairly simplified but very useful analysis, namely assuming that the level populations are all in local thermodynamic equilibrium. That simplifies the analysis considerably, but let's just see if we can justify that. So this compares the 3-to-2 versus 2-to-1 pixel by pixel, and the red lines here are lines of constant excitation temperature ratio. And so the line ratio equals 1 would be exact thermodynamic equilibrium. Most of the points fall just a little bit below that, but not very much, within 0.9 or so. So there's very little gas here, which seems to be very far out of thermal equilibrium. So I've argued that most of the gas in this cloud is within roughly 20% of LTE. And so with that assumption, we can then apply a relatively straightforward analysis to determine the gas temperature from the 2 isotopes. And so this shows temperatures ranging from, typically the green is in the range 10 to 20 kelvins, and there are hot spots up to 40 or 50 kelvins. So the warmest gas is in fact associated with the locations of the hot stars. So these little crosses mark all the late O and early B stars, which are also energized in the H2 regions, and indeed there's an obvious correspondence there. We can also calculate the optical depth from the line ratios of the isotopes, and this shows something interesting here. Now the crosses are positions of young stars that were derived by some of my co-authors on this paper using the all-sky surveys WISE and 2MASS. Unfortunately, there was no deep Spitzer observation of this whole cloud, but I'll show you something on the region right around S235 in a moment. But you can see there are lots of young stars closely associated with all these high column density or high optical depth regions, consistent with star formation occurring principally along the sort of almost a skeleton-like structure within the overall cloud. Now we can also, with some assumptions, make a map of the total column density of gas. And so that's what this shows. And notice it's a logarithmic color stretch. So it emphasizes the lower column density regions in solar masses per square parsec. And you can see that it ranges upwards of over 1,000, but the bulk of the regions are in a few hundred to 1,000 or so solar masses per square parsec. Now, I'd like to also zoom in and take advantage of a better census of the young stellar objects surrounding the region of sharpless 235, which has an O9 ionizing star, and then there are 3 embedded early B stars, which are producing compact or ultra compact H2 regions. And in fact, there is a whole cluster of young stellar objects around here. So let's zoom in on this region, which was studied by Luis Chavarria and a number of colleagues, I think including Laurie Allen at NOAO now. And they cataloged the young stellar objects using Spitzer observations as well, and this was part of the so-called Gould's Belt survey project, and deep images from the 4-meter on Kitt Peak with the new firm camera. And then they classified them all by evolutionary state. And so this shows the CO 2:1 13 CO integrated intensity. And now the young stellar objects, which the Chavarria paper classified as the class 1, so those are the youngest, are tightly confined to this highest column density regions. The class 2 objects are more widely dispersed, and those are older. And in our paper, we argued that could well be a consequence of diffusion of the youngest stars due to the random motions of the gas out of which they formed. But now we can also use the CO map LTE analysis of the temperature and the gas surface density to compare with another map that was produced in the Chavarria paper. So they actually produced not simply a catalog of young stellar objects, but also a map of their surface star surface density. So the contours here show from 5 up to 100 stars per square parsec based on an algorithm they used to derive these surface density or stellar surface density maps. And you can see that comparing with the gas surface density, which is now the color on the right here, there's a very good correspondence. So in fact, the white contours here correspond to gas surface densities, which would have an AV of 7 magnitudes. That's the outermost contour here, and 25 magnitudes, which are the densest cores of the molecular cloud. And they all correspond quite nicely to the maxima in the YSO surface densities. So now we can make a quantitative comparison looking at this is now the young stellar object surface density in stars per square parsec, averaged over a series of bins in gas density. So the horizontal lines here just show bins 100 solar masses per square parsec wide, going up all the way to 1,000. And on a log-log plot, sure enough, you get a nice straight line with a slope of about 1.6. So it looks like a nice power law. We can also plot the projected area distribution of the molecular gas. So this is kind of a structure function showing the logarithm of the area with a surface density greater than the value on the abscissa. And that's just plotted in a linear scale. So we have a log linear plot. A straight line means this aerial function is essentially an exponential. And this is the best fit here for the line that's shown. Well, that's interesting. But how can we convert this to a star formation rate? Well, if we take a mean mass per young stellar object in that field, and here I'm adopting a half a solar mass. This is basically using numbers that Neil Evans and his colleagues have proposed based on a lot of their C2D work, and an average age for the young stellar objects that are in that field of 1 million years. And admittedly, that's a nice round number, but I think it's justified. Evans et al. Have argued that the class 1 stage has a duration of about 500,000 years, and the class 2 about 2 million years. And there's a roughly equal mix of the two. So 1 million years seems like a reasonable estimate for the age of all the stars within that field, certainly accurate to no worse than a factor of 2. And so if we apply those to the power law fit, we can actually then get a star formation rate versus gas surface density plot. Now that brings up this interesting figure, which you may recognize from the very nice annual reviews article by Kennicott and Evans, which shows the star formation rate in solar masses per year per square kiloparsec plotted versus the gas surface density in solar masses per square parsec. And these are mostly averages over whole galaxies or even parts of galaxies. But if we overplot now, scaling the relation we just found for Sharpless 235, it looks like that. So it's sitting well above the galaxies, no surprise. This is, after all, a vigorous star-forming giant molecular cloud, but it has just the same slope as the global averages for normal spirals, which is from work that Rob did back in '98, the blue symbols here. So that's interesting. Maybe not quite clear what it means, except that perhaps nature loves a power law. But I think more interesting might be to compare our scaled relationship to recent numerical models of the graviton-turbulent simulations. And it turns out that this empirical fit actually matches some of the more recent predictions very nicely. So some work by Fedoroth and Klesson. And this shows a figure from a review by Padoan et al. In one of the Protostars and Planets. I think it's volume 6. So this shows the same log plot of star formation rate per year per square kiloparsec versus gas surface density. Again, a log-log plot. And the contours here now are from a whole series of simulations by Fedoroth and Klesson. And the contours enclose the inner one, 50% of all of the samples in their whole suite of simulations. And the outer contour is 99% of all the simulations, with 2 different assumed star formation efficiency rates. And if we now overplot our empirical relation, it looks like that. So that's very encouraging. It looks like the models, in fact, predict quite nicely what we actually observe in the case of Sharpless 235, modulo some uncertainty in the assumptions, but I think you can't move that curve or the green fit very well, very much. And so it's gratifying. I hope to the theorists that in fact the empirical derived from observations results seem to match quite nicely the predictions of the theoretical models. Okay, so just to conclude on this part, the surface density of young stellar objects seems to scale as about the 1.5 power of the gas column density. I think that's interesting because in Martin Schmidt's original paper, which is often cited as the Schmidt law, although that's, I think, a misnomer, it's really, and I'm sure Martin never thought of it as a law, it's an empirical relationship that the rate of star formation scales at something between the first and second power of the gas surface density, and indeed it's, in this case, exactly between 1 and 2. The distribution of the area function molecular clouds looks like an exponential function with gas column density, and making reasonable assumptions about the mass of stars formed and their lifetimes or ages, we actually get values that are in quite good agreement with some of the more recent numerical simulations. So the combination of the first two points here is that the gas column density, where the density is highest, is the area which dominates the formation of stellar clusters. And so it's really the combination of this scaling law coupled with the structure function of the giant molecular cloud that determines how vigorous the star formation rate is. Okay, so I still have a bit of time, that's good. So I'd like to now move on to one more recent paper. And this is something which has just been submitted to the APJ. The lead author is John Lewis, who is a graduate student at Harvard. He's been working with Charlie Lotta and myself and some other colleagues to study the so-called California molecular cloud and look at how the CO properties compare with the properties of the dust in the cloud. And in particular, he's shown that we can use CO depletion mapping to actually identify prestellar cores, cold cores within this cloud. So this is the so-called California cloud. The name actually was coined by Charlie Lotta, not because it looks like California, but because it happens to sit next to the famous California nebula, which is an H2 region. And actually, they're not physically associated at all. So it's just a coincidence. But this shows a Herschel map of the dust column density, and where the dust temperature and optical depth were derived from a series of multiband images using the PAX and SPIRE instruments. And so it goes very deep with the highest dust columns corresponding to about 60 magnitudes of visual extinction. So that's really something of a record almost, thanks to the sensitivity of Herschel. So we've mapped out the areas that are enclosed in the black and the blue, red regions here. And so we mapped those with the SMT using the same techniques I've just talked about. So each of these has a name associated with a Lens dark cloud. Over here is actually a BE star, Lick H alpha 101, and a small H2 region with an NGC number. And this region over here is sort of boring in a sense. There's not much star formation going on here except in a particular region, which is the subject of another paper I don't have time to go into today. But one of the things that John did in this work was to calculate a depletion factor, which looks at the column density of CO divided by the column density of molecular hydrogen. And so we can get this from the CO maps and this from the Herschel maps, assuming standard gas to dust ratios, and compare that with Yeah, I guess this is written right. So this is sort of from the interstellar medium, and this is the gas in the cloud. So a larger number here means a lower CO abundance within the molecular gas. And CO is a volatile element, so at very low temperature and high densities in molecular clouds, it tends to freeze out onto the surface of dust grains, or we say it's depleted. And this has been known about for a long time. And it's sometimes viewed as a handicap in using CO, but in fact, in this case, we've been able to use it as a way to find the dense, dark regions and actually catalog them. So this shows now the depletion factors versus dust temperature derived from the Herschel data. And as you'd expect, the depletion factor goes up at very low temperatures, meaning that only 10% or less of the CO is actually in the gas phase. 90% of it is frozen out onto grains at the very lowest temperatures. So this shows maps of the depletion factors in the region of that eastern side of the field near Lick H alpha 101. And the arrows just mark some of the deep depletion cores, which were then cataloged in this paper. So the paper has a catalog of 134 cores, which were identified by this depletion mapping. And in fact, 20 of them, it turns out, actually have a protostar, probably because they have infrared point sources in them. So we've been able to work out things like the radius, the mass of the core, the dust temperature, and also velocities and velocity widths from the CO observations. And so from that, we can compute a virial parameter, which involves the mass, the velocity dispersion, which includes both the sound speed and the non-thermal component, which we can measure directly from the CO, and the size, the radius from deconvolving the CO maps. And so we get a plot that looks like this of the virial parameter versus the mass of the core. And interestingly, as you can see, the more massive cores, most of them have a virial parameter less than 2, which corresponds to a core which is just gravitationally bound, but not quite fully virialized, and a few of them are below the alpha equals 1 value. The straight line here actually shows a prediction for pressure confined cores from a paper by Bertoldi and McKee some years ago, and it actually seems to fit the data reasonably well. Also, you can see this, the filled symbols indicate that the more massive cores are typically bound and typically contain a protostar, it appears. So that's an interesting piece of work which is still being refereed, and hopefully we will have a report, and you can watch for it on AstroPH hopefully before too long. So I'm just about out of time, so let me just finish by saying I hope I've convinced you today that even in this era of ALMA and $100 million annual operating expenses, we have right here at Steward 2 very cost-effective telescopes for doing single dish observations with sensitive receivers, and there's still an important role for them to play in studying all the properties of molecular clouds and star formation. So thank you very much. I'll stop there.
Thank you, John. Do you have any question? Please use the participant. You can raise your hand.
Question from Ian?
Yeah, thank you, John. A quick question actually about one of the factors that I think often gets ignored when people do column density calculations or total mass calculations is the filling fraction. Can you say anything about, since you have multi-transition studies of some of the clouds, what that must mean for the filling fraction of the CO emission within your beam?
I don't think we can say too much about that because we do see structures down to the resolution limit of which for the nearer C2D clouds is only a few hundredths of a parsec. So likely there could be structures smaller than that. Although I would say that the temperatures that we infer are pretty consistent with what you would expect from probably higher resolution dust imaging, or even perhaps some of the ALMA images. So I'm not sure I can make a very precise statement about that, but I would say, yeah, there could well be structure even certainly below the resolution limit, which is an argument for using the large area maps as sort of finding charts for higher resolution studies.
Okay, any other questions for John? I have one. So in the submitted paper you were talking about with the California Nebula, does your ability to show how whether or not a cloud has a protostar as a function of mass tell you anything about the star formation efficiency of that region?
Well, yeah, it clearly has to do with the sort of structure function that I talked about. And in fact, that was also observed by Charlie Lada and his colleagues, Alves and Lombardi, in another earlier paper, where they showed that that cloud has much less area in the highest column density regions. So the difference in the star formation rate between California, say, and the Orion molecular cloud, which is actually at a comparable distance and has a comparable mass, but 10 times the star formation rate, the difference is in the structure of the cloud. At the moment, at least, the California cloud has far less of the highest column density regions.
All right, thank you. Any other questions for John? If not, let's go ahead and thank him again for a wonderful.
Thank you, John.
Thank you, John.
Thank you.